Thank you very much for the invitation and for the interesting talk that we've already had. I'm going to talk about anomaly detection in networks. So this is joint work with people from the Alan Turing Institute, Andrew Elliott, Mihai Cucurindu, and also joint work with Milton Martinez-Luaces and Paul Rady from Accenture. There's a paper on the archive, and there's more recent work, which is not yet part of a paper, which is with a large telco. So there are two main motivations for this work. So the first motivation is financial fraud. So you've all heard about financial fraud. So financial fraud is a huge problem worldwide. So in the UK alone, it's estimated that the financial fraud is equivalent to the gross income of a small country. So so that's a big issue. So financial fraud is huge. So we are interested in anti-money laundering. So we think of financial transaction fraud. And of course, this is where networks come in, because we think of as accounts as nodes in a network, and then transactions between accounts as directed edges. And these edges are weighted by the transaction amount. The second motivation is from a large telco. Here we look at firewall data. So this is a different type of data set. This is an internal company network. They are, in particular, they're looking at their internal computer network and the firewall data in their network. So they've got a huge amount of data available. The network is accessed by many vendors every week, and they want to make sure that it's not attacked. So they want to spot anomalies. So anomalies could spell trouble. Anomalies also just could mean that something isn't running as well as it could do. And of course, manual detection of anomalies is complex, labor intensive. And so people want to have automated ways to detect anomalies. Okay. So what kind of anomaly are we thinking of? So we are thinking of anomalies as maybe a long path of transaction amounts or a ring of large payments with accounts shifting money between them. We could think of clicks of accounts that send money to each other. In the telco example, we could think of nodes which trigger many firewall events during the time series observations. Or we could think of groups of interconnected nodes which are involved in many firewall events. So we can come up with ideas what an anomaly might be, but really the typical anomaly is probably a new anomaly, something that we haven't seen before. So in some sense, we want to find the unknown anomalies. So of course, this is an old problem, very old problem. People have, there are many ideas on how to do this. So there are ways of detecting specific fraud, for example, using autoencoders, support vector machines, social network analysis, and other rule-based approaches. So you put in what you're looking for, and then you try to find it. Then there's the mesoscale fraud detection, where you're, so we're interested mainly in detecting fraud at the node level. If you're trying to detect a shift in the whole network, you can use, for example, community detection or embeddings or clustering or time series models and search for change points. People have also looked at spectral approaches to pinpoint anomalies, so localization of eigenvectors and matrix factorizations. The method that we are going to compare our results to mostly is oddball. So oddball is trained to detect 4 different anomalies in weighted networks, which is also what we're looking at. So the anomalies that could be described like almost a star, almost a click, heavy vicinities, where you've got weighted edges, and heavy edges. And it works like that it fits power laws to network node level statistics and uses that to compute an outlier score. So our work is building on these, but reflecting on the typical anomaly may not be known already. So we want to detect novel anomalies We want to use labeled data if it's available, so data where we know what an anomaly is. The challenge is we want to have a fast method which picks up small anomalies in large networks, and we want the approach to be transparent. So we want to be able to pinpoint why something is judged as an anomaly, if we can. So the idea is that we implemented is merging of different methods. So we use community detection for networks to first decompose the network into smaller networks, smaller units, because otherwise the very large networks are really slowing us down. And then we actually will go down to the sort of subgraph level, which was just mentioned. So we do quite detailed network comparison based on small subgraphs and spectral features to pick up small anomalies in these individual communities. And then we use these as well as some standard network summary statistics as input, as features for random forest to obtain a fast method. And we also actually take just the sum of all the features as a transparent method. So in total, we have got 140 features. So to assess the behavior of, and to create features, we use Monte Carlo tests. So you will all have seen Monte Carlo tests before. They're very intuitive. So you just randomize the edges of the network while you keep the degrees fixed. So that's the configuration model. So we keep the degrees fixed, we randomize the edges, and then we randomly shuffle the weights of the edges as well. And so this is our null model. And if you have got a deviation from this null model, we think something interesting is going on. We're going to go over that in a little bit more detail in a moment. Just to give you an overview of the data, for the financial network, it was really difficult to get data. So we have two synthetic network data sets. So first is one which we generated ourselves. It's based on directed Bernoulli random graph, where we've got random weights as well as randomly planted anomalies. And the second network is the network which was generated by the Accenture team, which was modeled after real networks. And the anomalies in this team were revealed to our Turing team only after the analysis. We also use a large firewall data set from a large telco, which does not have ground truth. So in the first two data sets, we have ground truth. The first one we planted ourselves, so we know what the planted anomalies are. The second one we were told after the fact. And the third one, we don't have ground truth. We did an inspection of the anomalous nodes and groups of nodes later on. But so these are sort of the three different types of data sets. So our synthetic data set is a weighted directed Bernoulli random graph model where we plant unusual structures. So we create a directed Bernoulli random graph, and then we draw edge weights uniformly from the interval 0, 1, and plant a random number of anomalies at random locations. So this is our null model. So these are the planted anomalies. So the first one is a long path, and the second one is a cycle. So this is a cycle of length 5, but we have different lengths. The third one is a star, directed star. The fourth one is a click. And the fifth one is some kind of feed forward structure, where we've got sort of one layer feeding into a second layer, feeding into a third layer. So for each of these anomalies, we draw a number between 1 and 20 to plant them. And we select the type and the number of nodes uniformly at random, and we place them uniformly at random on the network. And then on these planted anomalies, we place weights which are at the top end of the weights would be placed on the others. So we have uniform weights, but only starting from W up to 1, where W is chosen so that the expected number of each anomaly is less than 1 in the network without planted anomalies, because we want this to be anomalous. Right? Otherwise, if we see copies of this, even in a normal network, it's we detect something else. Then the second data set the number of nodes is fixed to 55,000. So this was constructed by Accenture. Each node is designed an in degree, which is normally distributed with mean 21 and variance 9, and then out degree, which is normally distributed with mean 19 and standard deviation 4. Now you might say, hold on, the normal distribution could be negative. Well, if it's negative, it's just set to 0. And also, you might say, well, it might not match up. So the sum of the in degrees might not be the same as the sum of the out degrees. So it's not really a network. So what they did is then just reduce the larger sum by deleting edges at random until the totals matched. So then they just do a stub matching thing. So each node is an in degree and an out degree and the corresponding number of stubs, and the stubs are randomized and matched. If there are self loops, the self loops are deleted, so it just swaps the self loop with some other node, but they don't mind multi-edges. And this happens until all the stubs are matched. And they added to their network a clique of size 8, where they had exactly one edge, so no multi-edge, and a similar clique of size 12, no multi-edges, a ring of size 4 with constant weights, a ring of size 10, a heavy path of length 5, which was sampled from paths that already exist in the network, but the weights were changed to make them heavy, and also a similarly heavy path of length 10. And the weights of the heavy edges are drawn uniformly at random between 0.99 and 0.9999999. And then they use as weight the quantile, so the value that would be required to obtain this number as a percentile from a normal with mean 1,000 and variance 200 squared. So it's not the kind of model we would have come up with, but this was revealed to us later. That's how they constructed it. The third data set is just a firewall data set, so I can show you here a pretty picture. So this is a data set of spanning about 2 weeks. 2 computers are linked by a directed edge if a connection between the 2 nodes was recorded as a firewall event. We've got about 160,000 IP addresses. The number of daily firewall events ranges from 2.7 million to about 7 million, spanning about 2 weeks. So we've got daily data sets. And this is just one representation. And here's the pipeline of our method. So we have our input method, of our input network. And on this input network, we carry out community detection. We also carry out basic tests like just degree. And with the community detection, it turns out when we separate the network into communities, you may have spotted that you will destroy long paths. You may destroy long paths because we just cut through them. So we've got a pathfinder method as well. For the community detection, once we've got our community detection, first we have a test about community detection to see whether we've got anything that's not just configuration model. We've got localization tests for spectral summaries. And we've also called a test which is called based on net EMD, which is the Earth mover distance between summary statistics of small subgraphs. And we combine all of these in 2 ways. One is the random forest, and the second one is feature sum, and get an output score. So this is our big framework. So let me tell you a little bit more about these this method. So the first module just performs some basic tests for deviations from the null model. And then, so our basic tests are these Monte Carlo tests. For each test, we get a p-value, and we can convert the p-value into a score so that all the tests are, the scores are of similar order of magnitude. And then it divides the network into communities and adds a pathfinding method to ameliorate this effect of splitting the network into communities. So for the basic statistics, the deviations are assessed using a Monte Carlo test with the shuffled weights and configuration model. And if the p-value of the Monte Carlo test is less than 0.05, we report a score, and the score is then the standard normal percentile of 1 minus this p-value. So the probability that a normal would be at least as large as 1 minus this p-value. And otherwise, we just report 0. So we've got scores which relate to normal percentiles of p-values. And this way, we unify all the different statistics to live on the same score sense. And for community detection, we use Louvain modularity. And in order to avoid cutting through long, heavy paths, we use an augmentation trick from spectral analysis. So when we've got a path of length 2, and each edge in this path is really heavy, so it exceeds the 99th percentile of the weights, then we add an extra edge along these paths, so we don't cut through this path so easily with the community detection. And then for each community, we use a range of statistics, summary statistics. So we use the density, we divide the density by the density of the full network. We divide the density by the size times the density of the full network, and by geometric averages. So we look at various versions of the averages and the densities and the geometric averages of the weights. And for the Monte Carlo test, what we do is we start with the configuration model and carry out community detection on the configuration model to incorporate this step into the test. Then we pick one community from each of these networks randomly, and we assess statistics in this non-augmented network. We don't do the heavy parsing to obtain the null distribution. And to avoid to account for long paths possibly being split, we also have a separate feature for finding long paths. So we start with a path of length 3, and we extend the path until they've reached a length of 20, if that's possible. And then we assign a score to these paths and get a p-value and use the standard normal quantiles to convert it into a score. So the second model looks at more detailed network comparison. So the first one was just community detection and the pathfinder and the general statistics. So here we include the nodes from this community detection steps, but also more detailed network comparisons. So the first set of more detailed network comparisons are based on the Earth mover distance. So the Earth mover distance is just the integral over the absolute difference of two univariate cumulative distribution functions. So it's the amount of work that's needed to shift one mass from one point to another point. So it is really Earth moving distance. So the Earth mover distance, if we got finite different variances, we just divide these distribution functions to scale so that the underlying distributions have the same variance. And we allow the distribution functions to shift because we want distributions to be viewed as similar, even though they might have a different center of mass. As long as they've got the same shape, we want to have a small distance. And so we can look at the distributions of, say, the number of triangles and the number of all kinds of small networks, and get the Earth mover distance between the observed distribution and the one which we would get from our configuration models. And then so we get this for different properties, and then get the Earth mover distance between the two graphs, the net EMD, as we call it, by just summing over these individual Earth mover distances. And there's an implementation available of this method at a GitHub site at the Turing. So the features that we are looking at are directed subgraphs. So here are different directed subgraphs on up to 3 vertices. And we just count the number of the copies of subgraphs in which this node is involved in. So, and you see that for graphs with different densities, you would get different counts. But if the graphs come from the same underlying principle, you would expect the count distributions to have similar shape. So the empirical distributions we look at also are in degree, out degree, sum of adjacent weights, and weighted directed subgraphs of size 3, and also features which are based on the top 5 eigenvectors in this augmented network. And then we carry out this Monte Carlo test and get our scores, again with the top 5% cutoff. So these are the subgraph count statistics. We also use spectral localization statistics. So spectral localization means that a large amount of the mass of an eigenvector is placed on a small number of nodes. So that means that if that is the case, the small number of nodes will be somewhat different to the other nodes. So would point towards an anomaly. So we are looking for this kind of thing. So these nodes might be good candidates for anomaly detection. And because we can't, so we want to explore many, many features in order to get the best ones. And so we look at different Laplacians. So if we've got a weighted, possibly directed adjacency matrix, we take we take W plus W transposed to symmetrize it. And then we look at the combinatorial Laplacian and the random walk Laplacian, where the diagonal matrix with the degrees D features in both of them. And the eigenvectors are always normalized to have Euclidean norm 1. Then for each of these communities, we look at localization separately. We look at the top 20 and the bottom 20 non-trivial eigenvectors of this symmetrized matrix, and as well as of these Laplacian. And when the network has fewer than 20 nodes, we just consider as many eigenvectors as possible. And then we compare with what we'd expect at random. And we assign, if we see that we've got localization, so something that's not expected at random, we assign a score to the nodes which carry most of the weights. So this gives us 140 features in total. So what do we do with them? So far, each of these statistics just produces a score. And one method which we do is we just sum up the scores. We call this the feature sum. So the feature sum has the advantage of being really transparent. So we know what goes in it. We know if we change one observation, if one edge is changed, we can exactly track how this would affect the overall score in principle. But we also use a random forest as a simple classifier where we can still look at the importance of the different features. So we generate training data from our generating model with the Bernoulli random graph with different levels of P and W, such that each anomaly has an expectation less than 1 in the network without the planted anomalies. So depending on the density of the network, the weight W, the cutoff will have to change in order to satisfy this condition. And then we construct 100 networks for each of the parameter combination and take the first 70% as training, the remaining 30% is test set. And then we have 2,700 networks and use our pipeline, perform feature selection, and we prioritize features that perform well across the ensemble of parameters regimes. So this is only for our first data set where we know the ground truth. So then we combine the data from each of these regimes and fit a random forest. So maybe can, so we use a scikit random forest regressor and just rank the features using the scikit ranking, taking the average over all the different parameter regimes P and W to rank the feature. And then we try to look for an appropriate cutoff for looking for a large jump in the average rank in this rank plot. So here's the rank plot. Do you see a large jump? Well, so we decided here where the red line is, that's a large jump. So it's not impressive, but it's better than nothing. And then we can look at so this gives us 44 features using this jump. So of these, most of them relate to localization, and then about half of the next about net EMD, the basic statistics like degree come in quite a lot, and path and community detection density are not so important. And the underlying statistics are mostly related to different random matrices. Motif counts somewhere here in the middle. I'm very keen on motif counts. So I was a bit sad to see this, but and so we can see which kind of statistics have which contribution. So here's just putting this down again. So here's as I know we don't have that much time left. So here's a plot. So what we can do exactly, can look at each parameter regime and see which are the most important features in which region. So these are colored. So if we've got very sparse networks, then the paths of length 5, 6, and 7 are quite important. And when we've got larger networks, the localization and Laplacian features can start to be quite important. So the method is transparent in this way, in that we can actually slice and see what happens in which parameter regime. So how do these classifiers actually do? So here are, so the blue line on top is the random forest model. The yellow line is the feature sum model. So the feature sum actually, so this is on our generated data where we know the ground truth. So the feature sum does actually surprisingly well, given that it's really just the sum of the features. And so the green line here is oddball. Now, but oddball is of course constructed for a slightly different task. So it doesn't have these planted anomalies, so it doesn't do so well. And then we also look at the random expected score, which is the red. So we've got upper bounds and lower bounds in the different parameter regimes. And so they all do better than random, as one should. And for the Accenture data, so here, the plot is slightly, so it's tilted. So the red line here is what would be expected at random. And we see that, so on average, the random forest does very well, and the feature sum does very well. So random forest is this yellow line, and feature sum is this blue line. But in one regime where we got sort of not a huge average position score, oddball performs really well. So I must say, here we adapted oddball slightly to fit into our setting. But if you want to have sort of higher precision, higher average precision scores, feature sum is doing really well. Okay, and we can look at recall and precision, and you see here for oddball, the recall just never goes up to 1. So even with the number of nodes, whereas for us, the recall both for feature sum random forest does converge to 1, and the precision of course starts at 1 and then goes to 0 the more nodes we have, as expected. So I said originally that what we want to do is we want to detect unknown anomalies, and we do. So here's an example which we find in the Accenture network. So this is a huge star with a couple of loops. which is not one of the structures which we planted. Looks nice. And in the firewall data, we found this structure, again, one which wasn't planted. So you have two nodes here on the left and on the right, and then we have two layers of nodes which try to connect to each other. Red means that the connection was blocked, green means the connection was allowed. So these two nodes are connected through a green connection, but all these intermediate layers were stopped. So for the firewall data, what we did, we just listed the potentially anomalous nodes ranked by score. What we found first when we looked at the data, that there were data collection issues, which we highlighted, which was taken on board. So this is probably when you deal with real data, you're used to that. You know, sometimes you just find something isn't the way you expected it to be in the data. But then also through this analysis, we spotted configuration issues. So some machines were just badly configured, and they contributed to a huge load on the firewalls. So this was reducing the load on the firewalls, and also we raised some issues which may be related to potential attacks. They have been followed up on. So this is what we've done. So we have this anomaly detection method. We have 100 features and 2 scores. Feature sum is fully transparent, and random forest is sort of transparent. And then we have our benchmark set, where both feature sum and random forest perform well and perform oddball, and random forest outperforms feature sum. But on the Accenture model, feature sum, random forest actually both perform reasonably well. And when you rank the nodes, we find they find more than 90% of the embedded anomalies within the first 2% of nodes. And feature sum, in this respect, outperforms random forest, and both outperform oddball. For the firewall data, I don't have so nice statistics because we don't have ground truth. I can just say it yielded useful information. So what's next? So the random forest classification is a bit chunky, and there are other methods available. So all these AdaBoost, XBoost, autoencoders. Yesterday, I learned about GraphGym from Jure Leskovic's group, which are worth trying out. Keeping in mind that we do want to have transparency when we can. Incorporating time dependency, we haven't really done that. We just looked at several networks. So which is partly why I asked previously about multi-layer networks, because that might be an approach. Instead of having this configuration null model, we could think of a Bayesian approach, although Giuseppe Ronconi is convincing me that the configuration model is a good one to use, although there might be a slightly better one to use instead. Exploring further the statistics that are driving the performance in order to refine the method, because not all statistics maybe should get the same weight. So maybe we can do a little bit more about that. And finally, including fairness awareness. This is something we haven't done at all. So this is detecting anomalies somewhat blindly to the problem of interest. But of course, fairness is a huge issue. So if for some reason our algorithm detects something where the results are discriminating against, say, a certain type of node. So if nodes belong to individuals which have certain characteristics, that has to be assessed and included. And there's a paper by Shekhar Shah and Akuglu from last year, which has a promising approach. Okay, that's all I wanted to say. Thank you.
Thanks, Professor, for the presentation. So do we have any questions?
I should say that one of my co-authors, Mihai Cucuringu, is also going to have a poster at the poster session, which is following up, but on a slightly different topic.
Okay, so we have a question here. So The question goes like this. So in general, the anomaly detection data set may have high class imbalance. Any approach to deal with that?
Sorry, can you repeat it? I didn't quite catch that. Oh,
Okay, so
my high class imbalance.
yeah,
Yes, I mean, that's why we actually developed this method, because we are looking for needles in a haystack. So we have, most of our nodes are normal. This is a very fine-tuned way of dealing with a high class imbalance. It's a good question. It's exactly the point that we're trying to address.
okay, sure, thanks. So thanks for the presentation again. And
Thank you very much.
so next up,